Hello students, let us start our new session of chapter number 7, Systems of Particles and Rotational Motion. Let us start the session with the topic angular acceleration. Here, kinetic variables, we are having linear displacement s, velocity v in translational motion. For the angular displacement, we denote as a theta, and angular velocity we denoted as a omega. So angular acceleration alpha, that is a rate of change of angular velocity with respect to time, that is a d omega by dt. If axis of rotation is fixed, then direction of omega and acceleration is also remains fixed. So in the case of vector equation, d omega by dt equal to alpha for the scalar equation. Now let us understand torque and angular momentum. This torque and angular momentum are defined as a vector products of two vectors. Let us understand them in detail. Let us take first torque. Torque is also known as a momentum of force. If body is fixed at a point, has only a rotational motion, and rotational analogy of force in linear motion is a momentum of force, can be defined as a torque or couple. If a force acts on a single particle at point P, as we can see in the diagram, whose position from the origin is available at a distance r, the momentum of force acting on the particle with respect to origin can be defined as T equal to R cross F. So here the momentum of force or torque is a vector quantity which can be symbolized as a tau from the Greek letter. So magnitude of torque tau equal to R F sine theta, having a dimension m L square t raised to minus 2. Its dimension is same as a work or energy. Momentum of force is a vector while the work is scalar. Its SI unit of a momentum of force or torque is a Newton into meter. The magnitude of the torque or momentum of force tau equals to R sine theta into F, so equal to R perpendicular component into F, or R into F sine theta, so R into perpendicular component of F. So R perpendicular means R sine theta, or if we take that R sine theta means the perpendicular distance of line of action of F from the origin. And if we are taking F perpendicular component, that is F sine theta, that is a component of F in the direction perpendicular to R. So that if tau is 0, if R is 0, F is 0, or theta equal to 0 or 180 degree. R cross F, that is a vector product. If the direction of F, the given force, is reversed, then direction of momentum of force, the direction of torque also gets reversed. If the dimension of both R and F gets reversed, then direction of torque remains same. Now let us understand another component, angular momentum of a particle. Angular momentum is a vector product. It can be referred as a moment of linear momentum. Here let us take a mass m and linear momentum p at a position r from the origin. Angular momentum is denoted as L. So here we are having the equation angular momentum L equal to R cross P, and its magnitude L equals to RP sine theta. That theta is the angle between R and P. So L equal to R perpendicular component with P, or R dot P of perpendicular component. So r perpendicular component, that is equal to r sine theta. It defines that perpendicular distance of directional line of P from the origin, and P perpendicular component, that is equal to P sine theta, is the component of P in the perpendicular direction to R. L equal to 0 if linear momentum P is 0, if particle is at the origin R is 0, or if the directional line of P passing through the theta angle is 0 or 180 degree. Let us differentiate this equation with respect to time, that is L equal to R cross P. So that rate of change of angular momentum will give you the torque. So del dl by dt equal to d by dt R cross P. Now we are taking a product rule for the differentiation, that differentiation of R cross P with respect to time, it will give you dr by dt cross P plus R cross dp by dt, and dr by dt, that is the velocity v. So here we are taking, and P equals to m into v. So let us substitute P equal to m into v. M is constant, so that would be dp by dt equal to m dv by dt. So here that dv by dt will give you acceleration a. So ma equal to f force. So let us substitute all the component derivation, that r cross dp equal to r cross f. And as we already learned the component r cross f, that is a torque tau. So here dl by dt, that is equal to torque tau. Now let us take another topic, torque and angular momentum of a system of particles. So if we want to get a total angular momentum of system of particles for a given point P, we need to add vectorially the angular momenta of individual particles. Let us take n particles. For the ith particle, Li equal to Ri cross Pi, and P equals to Mi Vi. So capital L, the total angular momentum of the system of particles, that is summation of Li, that is equal to summation of Ri cross Pi for the I different values 1 to n. And let us differentiate this, that dl by dt, that is a d of summation of Li by dt equal to dl by dt, that gives you the torque. So here the torque acting on the particle Ti equal to Ri cross Fi. Fi is the force on the ith particle, is the vector sum of the external forces acting on the particle and the internal forces exerted on the particle of the system. So here let us separate the contribution of external and internal particles. So we are also having the torque external plus torque internal. So torque external equal to summation of Ri cross F external, and torque internal equal to summation of Ri into F internal. So here the internal forces of the total torque, that is affected with the zero value, as the torque resulting from each action and reaction of pair is 0. So internal torque value is 0. So total torque is available due to the external torque. So that's why dl by dt we are having torque external. So rate of change of total angular momentum of a system of particles about a point is equal to the sum of external torques acting on the system taken at the same point. Now let us go through the another topic, conservation of angular momentum. If torque external is 0, then dl by dt is 0. It means a total momentum L equal to constant. So if external torque onto the system 0, then momentum of the system conserved, that is taken by the constant value. Let us take for the three scalar equations. Lx equal to k1, Ly equal to k2 and Lz equal to k3. So Lx, Ly and Lz are the component of total angular momentum of vector L, and k1, k2, k3 are the constant values. So the total angular momentum is conserved, means each of these three components should be conserved. Let us understand with the example. Find the torque of a force 7I plus 3J minus 5K about the origin. So the force x on a particle whose position vector I minus j plus k. So position vector r equal to I minus j plus k, and force is 7I plus 3j minus k. So torque tau equal to r cross f. So ijk tx ty rx ry ij rj and fx fy fj. So likewise, let us substitute the values in a matrix and solve the matrix. So we will get tau equal to 2i plus 12j plus 10k. Now let us take another example. Show that the angular momentum about any point of a system single particle moving with constant velocity remains constant throughout the motion. So here let us take a particle having its velocity v at point P at time instant t. Now we are going to calculate its angular momentum of a particle of an arbitrary point O. So here angular momentum L equal to r cross P and P equals to m into v. So L equal to r m v sine theta, and theta is the angle between r and v. So here the particle changes the position with time, then line of direction of velocity is the same. So OM equal to r sine theta constant. The direction of L, the angular momentum, is perpendicular to the plane of r and v, that is into the page of the diagram. So the direction will not change with time and L remains same in magnitude and direction. It means it conserved. Now let us understand another topic. Equilibrium of a rigid body. A rigid body is said to be a mechanical equilibrium if its linear momentum and angular momentum are not changing with time. So the total force, that is the vector sum of the forces on the rigid body, F1 plus F2 up to Fn, that is the summation of Fi from 1 to n, is 0. If the total force on the body is 0, then total linear momentum of the body does not change with time, and it will give you the translational equilibrium condition of the body. And the total torque, that is a vector sum of torques on a rigid body, is 0, then the total torque on the rigid body is 0. So if total momentum of the body does not change with time, it gives the condition for rotational equilibrium of the body. So if the translational equilibrium condition holds for a rigid body, then shift of origin does not matter. That is the rotational equilibrium condition, that is independent of the location of origin about which torques are taken. So here these values are vector quantities and can be equivalent to the scalar equation. Summation of Fix is 0, summation of Fiy is 0, summation of Fiz is 0. Likewise, summation of torque in x is 0, summation of torque in y is 0, and summation of torque in z is 0. So here we are having a 6 independent conditions should be satisfied for the equilibrium condition of a rigid body. From that, if only 3 conditions would be satisfied, can be acceptable. 2 of these conditions are based on the translational equilibrium, that is the sum of the components of force along the 2 perpendicular axes must be 0. And third condition related to rotational equilibrium, in which the sum of the components of the torques along any axis perpendicular to the plane of the force should be 0. So, a body may be in partial equilibrium, it may be in translational equilibrium and not a rotational equilibrium. Or it may be only in rotational equilibrium and not in a translational equilibrium. So let us see diagram and understand that. In diagram A, the system will be in rotational equilibrium, in which forces are applied on point A and B, both are in same direction, means rotational force is given, one is a clockwise direction and another force is given in anti-clockwise direction. So here forces are not 0. It means translational condition is available, but this rod will not rotate. It means rotational equilibrium will be defined. In diagram B, we can say that at point A, force is available at downward direction, and at point B, the force is available on upward direction. So their equivalent total force affecting on the rod is 0. So translational equilibrium is available. But one force at point A is available downward anti-clockwise direction, clockwise direction, and at point B the force is available upward at anti-clockwise direction. So the rod will rotate. So rotational equilibrium is not available. So in any way it undergoes a pure rotation. So here a pair of forces of equal magnitude acting in opposite direction with different lines, which is give you the action of torque, which will give you the pure rotation without a translation. That can be defined with the diagram with examples. In first diagram, as onto the jar, while we want to open or close the lid by our fingers and thumb, we are providing a force that will give you only rotational condition by the torque, and translation condition is not available. It means translational equilibrium is available. In the second diagram, we are taking a magnetic needle, or its magnetic field if we want to define. It means N pole moving and S pole moving, both are in opposite direction, but its translational equilibrium is available. Let us go through the example for the same. Show that moment of a couple does not depend on the point about which you take the moments. So let us consider a couple as shown in figure acting on a rigid body, having a forces F and minus F on point B and A. These points having the position vector R1 and R2 from the origin. So here its momenta is available R1 cross minus F plus R2 cross F, that is equal to R2 cross F minus R1 cross F, that is equal to R2 minus R1 cross F, will give you the sum of moments of two forces making the couple, making the torque. And here R1 plus AB equal to R2. So AB equal to R2 minus R1. So it will give you the AB cross F. So here we can say that is independent of the origin. the point about which we are taking the moments of the forces. Here we are going to end this session. Hope you understood. Thank you.